Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about vectors, or like an introduction to vectors. What are they? What's the anatomy of them? And we'll also get into some addition of vectors by the end of this. But there's going to be a part 2 to this, and in that one we will cover scalar multiplication, subtraction of vectors, the dot product, stuff like that. Work. Okay. Anyway, the motivation for vectors. So vectors are a powerful visualization that help conceptualize stuff like force, velocity, computer graphic projections, or vector graphics, and really anything dealing with a motion of an object along with its direction. So the examples we're going to be talking about today mostly involve aircraft, but you could do this for boats, right? Watercraft, anything with motion and a direction. So like a tennis ball is another example. The working definition that we're going to use for vectors is basically a directed line segment. And to be a little bit more specific, it represents a vector quantity, which is something that has a magnitude or a length, right, is another name for magnitude, and a specific direction. So for example, let's say that a plane flies westward at 425 miles per hour. 425 miles per hour, that's the magnitude of the vector. And westward is the direction. So visualized, right, this what is really a velocity vector looks like this, right? This is a representation, it's a directed line segment of a westward motion at 425 miles per hour. So this is the plane's velocity vector. The anatomy of it is that it's got an initial point and some terminal point. And the notation for a vector is really three different things. And I tend to go with the harpoon notation myself, but this is supposed to be like a bold, kind of fancy lowercase v. This is a v, you know, with the actual vector over it. This is what I call the harpoon notation. I like that one particularly. So that's pretty much what I used exclusively for this video. But then suppose that you know the terminal point and the initial point. I said that backwards. But then, so then you could say, okay, well then the notation could actually be written as MO with the vector notation over it, or MO with the harpoon notation over it. All right, now there's some cool facts about vectors. The first one is that relative size for vectors matters. So, you know, we had this westward bound plane at 425 miles per hour. Let's say that we also wanted to put in this same picture a northbound plane that's traveling 212 miles per hour. Well, it is visually going to be shorter, right? That's the thing about, that's what I mean by relative size of vectors matters. This is a smaller length than this because it's traveling at a smaller speed. So relative size is definitely something that matters, right? This one's noticeably shorter. The second thing is that vectors do not have a position. They only have direction and magnitude, which means they're not really bound to any particular place on the plane that you've drawn them on, right? And plane, not the flying plane, right? The Cartesian sort of plane. So I could pick this up and move it somewhere, right? I could take this vector v and I could translate it somewhere else and call that vector u, right? And they're the same, right? We could make the claim that v is equal to u. Vector v is equal to vector u in this case. Because they're not bound by position. I could move this directly on top of this and then it would literally be, right? You'd physically be able to see that they are equal. Which means you can also move them so that the terminal point, the initial point is coincident with the origin, right, of the Cartesian plane, and that's called a position vector. Okay, now position vectors are really nice because they help us define other key characteristics of vectors, which I'll just quickly go through. The first is that we can actually say the point that it's kind of ending at. We can give the terminal point a coordinate, a1, a2 in this particular case. But if you just say, okay, well, here's a vector that points towards the point a1, a2, how do we differentiate? Like if I just say, here's a1, a2, how do I know we're talking about a vector if this is the only context that I'm giving you guys? Well, instead, we use the angled brackets. And if I'm giving you something as an angled bracket, then you know, oh, that's a position vector, right? Its initial point is 0, 0. Its terminal point is a1, a2 on the Cartesian plane somewhere. I drew it in quadrant 1, but it can be anywhere. A position vector has what we call a horizontal component and a vertical component, and it's really just the x, y coordinates of that thing. We're just giving them a fancy name, with the vertical component being the y coordinate and a horizontal component being the x coordinate. Vectors also have a direction angle, And it's a normal angle measure, so it's a counterclockwise rotation away from the positive x-axis, right? Just like a normal angle, just like on the unit circle. So not like bearings, which is a clockwise rotation away from due north. That's a bearing. And then there's a length of the vector, and we're going to call that the magnitude. Okay, magnitude is given these kind of double absolute value looking things. That is mathematically, that's what magnitude, that's the notation for a magnitude. And it's in this case context, we're using it as like a length. Now we could find a formula for this length, right? I mean, we've basically constructed ourselves a right triangle here. Even more to the point, we could just use the distance formula, right, to figure out what that is, right? The distance formula is derived from the Pythagorean theorem anyway. And plus we've used the distance formula before, right? Anyway, it's the square root of x2 minus x1 squared plus y2 minus y1 squared, except that in this particular case, we've got x2 and y2 both as 0. And that, of course, is because the initial point of the vector is the point 0, 0. So if we have a position vector that we want to find the magnitude for, we're just going to use the formula magnitude is equal to the square root of a1 squared plus a2 squared. All right, and then the last thing to know about magnitude is that if you find the magnitude of a vector is equal to 1, that thing is called a unit vector because its magnitude is a unit. Okay, we can also calculate the direction angle. Because we've created ourselves a right triangle, notice that the tangent of theta here is opposite over adjacent, so it's a2 over a1. So simply taking the arc tangent of both sides gives us that theta is equal to the tangent inverse of a2 over a1. That one is pretty straightforward. We can actually extend this idea to find vertical and horizontal components as well, using right triangle trig. We set up a ratio using tangent already, but notice that the cosine of theta, right, is the horizontal component divided by the magnitude. The sine of theta is the vertical component divided by the magnitude. So if you wanted to solve for a1 and a2, you'd have to multiply both of these equations by the magnitude of v, and you would get this. The horizontal component can be found by multiplying the magnitude by the cosine of the direction angle, and the vertical component can be found by multiplying the magnitude of the vector by the sine of the direction angle. So there is a ridiculous amount of information on this screen, but these are all the main formulas that we're going to use for today. Finding components, calculating a direction angle, finding the magnitude. So let's do some examples. All right, so for example 1, we're going to find the magnitude and direction angle for vector v, which is given the position vector 3, negative 5. So first thing we should do is graph this thing, right? 3, negative 5, that's in quadrant 4. So our direction angle is going to be something that's bigger than 270 degrees, right? We can kind of guesstimate that right off the bat. Magnitude is always a positive length, so we should be getting something that's positive for the magnitude, but we're just going to instantiate the formulas that we just looked at. Starting with the magnitude, we know the magnitude of v is going to be the square root of horizontal component squared plus vertical component squared, which gives us the square root of 34, which is about 5.83. Done. Magnitude we can check off. All right, now here's the thing about the direction angle, right? We can definitely say that the tangent of theta is equal to negative 5/3, right? Because we've constructed a right triangle. We're on the Cartesian plane looking at theta. This is just the definition of tangent in general. But if you take the tangent inverse of both sides, you're not going to get theta. You're actually going to get this thing. You're going to get alpha. Well, that's fine, because we know that theta is just going to be 360 degrees plus whatever this negative angle is, because we're going to get a negative angle. Remember, tangent inverse only has a range of negative pi over 2 to pi over 2, except that we're not using radians in this particular case. I'll probably use degrees. So really, it's negative 90 degrees to positive 90 degrees. We can forget about the radians in these contexts, since pilots that fly airplanes typically don't say, all right, go ahead and fly at a bearing of pi over 4. They would usually just say fly at a bearing of 45 degrees. Anyway, I digress. The point is, we can still do this. You can find alpha, but you have to realize that that's not the direction angle of this vector. The direction angle will be that thing plus 360, because you need to go around again so that you can get theta, right? And it turns out that it's 300.97 degrees. Now, by the way, we don't have to necessarily do this to find the direction angle. In fact, this is actually a really good opportunity to use a reference angle, right? We could still say the tangent inverse of negative 5/3, but then say instead of that being equal to alpha, we can say, oh, that's the reference angle, right? The absolute value of that thing is going to be our reference angle. Okay, so you'd actually get positive 59.03 degrees, and then you're like, okay, well, to find the quadrant 4 equivalent of that angle that has this thing as its reference angle, which happens to be alpha on this picture, then you would just do 360 degrees minus 59.03 degrees, which will still be 300.97 degrees. Anyway, back to the examples. Okay, example 2. Let's say vector W has a magnitude of 27. I didn't bother putting units on this. It's just 27. And a direction angle of 155 degrees. Write the position vector for W by finding its horizontal and vertical components. Okay, so at least we know its direction angle, right? 155 degrees, that's in quadrant 2 of the unit circle. So I just put it here. And then we also know the magnitude is 27, and we're basically trying to figure out what is the position vector for this thing. Right? We need to know what are the coordinates. What do we end up here? Right? What's the horizontal component and what's the vertical component? Right? We can find those things. In fact, we're just going to find them both at the same time. Right? Here's the formulae for the horizontal component and vertical component. A1 is the magnitude cosine of the direction angle. A2 is the magnitude of the vector times the sine of the direction angle. Just kind of doing them both together. Magnitude's 27, theta is 155. You plug this stuff into your calculator, make sure that you're using degrees, and you should get negative 24.5 and 11.4. So that is the position vector for W. Example 3 is more just like a kind of a the more you know situation, like just like an FYI, a public service announcement, a PSA. Suppose P has coordinates -3, -4, and Q has coordinates 2, 5. Let's say we wanted to find the position vector PQ, basically, right? So what's the position vector when we have this thing? Which means we need to put this thing in what I would call a standard position, but more like a position vector position. Anyway. There's a couple ways to do this. You know, when the numbers are this small, I think it's fair enough to just say, we'll just move it, you know, shift it in such a way that you get P to be coincident with the point 0, 0. In this case, it means you can go up 4 units. So I did that. And then I noticed, oh, okay, now I need to go 3 to the right. So I did that. And I just kind of added, you know, the coordinates, you know, what I was shifting to the coordinates here to get the P to be 0, 0, and it happened to be that Q is 5, 9, so then the position vector is 5, 9. The other way to do it is to just find the distances. Find the vertical distance between P and Q, find the horizontal distance between P and Q, and that's your position vector. So if I can find this length here, which I can just use the vertical distance formula, 5 minus, you know, really it's y2 minus y1, right? It's the change in verticality. Is that a word? I'm going to use it as a word. 5 minus -4, which is actually 5 plus 4, so you get 9 there. And then the change in horizontal position, right, is x2 minus x1. That's 2 minus -3, which is going to be 5, so we get 5, 9. That's probably the easier way to do it, especially if these numbers are really, really big. Then it's harder to just visually shift stuff around. Just use the x2 minus x1 to find your horizontal component and y2 minus y1 to find your vertical component. All right, let's talk about planes again. So suppose that a plane is flying with an airspeed of 397 miles per hour at a 40-degree bearing. So 40 degrees due north. So this is not a direction angle. We're going to have to keep that in mind. At the same time, there's a 45-mile-per-hour easterly wind that's acting on the plane. Easterly wind means that it's blowing east, right? It's blowing to the east. Future mock here. No, that's not what easterly wind means. Easterly wind, in fact, means that the wind is blowing from the east. I actually went ahead and changed it to westerly wind, re-recorded this whole thing, and found out that the audio was all messed up. So I'm going to not do that again. Keep what I have here. The only problem is it's going to say easterly wind for the entirety of the rest of this thing. So just know that I really mean a westerly wind and not an easterly wind. Because again, easterly means blowing from the east, which actually is a westward wind. And a westerly wind, which is what I wanted to use here, is a wind that's blowing from the west, so it's blowing west to east. Okay, let's get back to it. And I hope you're okay with annoyingly seeing the incorrect terminology for the type of wind that we're talking about for the rest of this example. Enjoy. Okay, so first let's draw a picture of what's going on here. Here's the plane's airspeed vector. It's got a bearing of 40 degrees. We are going to have to figure out what its direction angle is here pretty soon. But then there's also this
westerly
wind of 45 miles per hour. All right, now here's the thing. This 45 mile per hour wind is going to change both the speed and the direction that the plane is flying. We need to figure out then what is the true bearing of the plane and what is the true speed, right? What's the true magnitude of the plane's airspeed vector. To do this, we're going to add these two vectors. And when you add vectors, you position them in a head-to-tail arrangement. Now, there's always two ways to do that. I happen to move the wind speed vector, the tail of the wind speed vector, to the head of the airspeed vector, right? The plane's airspeed vector. The other way to do it would have been to take the tail of the airspeed vector and moved it to the head of the wind speed vector. I probably would have put this in standard position so it would look like this. Then I would have moved this one here. But the point is, we would have ended up at the same place, right? And that's the cool thing about this head-to-tail stuff. It doesn't matter which one you move. Just make sure one of them's in a position vector, right? Make sure one of them's at the origin, 0, 0. That's just going to make things really easy for us. And then just move the other one. Okay, now the diagonal that connects the tail of the airspeed vector to the head of the wind speed vector, that thing is called the resultant vector. And the easiest way to think about it is that it's the diagonal created by moving the vector's head to tail in both orientations. It's the diagonal of the parallelogram that's formed between the head to tail positions. That's your resultant vector. That's called the parallelogram rule for adding vectors. The resultant vector between the addition of two vectors is the diagonal between the parallelogram that's created when you move these things head to tail, when you move the things you're trying to add in a head to tail orientation. And then that is the sum of those two vectors. C is the sum. That's how you add vectors. So now we want to find the magnitude and the direction right angle for C. This way we can figure out what is the ground speed of the plane and its true bearing, right? Direction angle is going to be its true bearing. Magnitude for C, that's going to be its ground speed. It's going to be how fast it's actually going when both forces are affecting this plane. The engine, vector, the airspeed vector, and also the wind speed vector. So we need to know this. We need to know the horizontal and vertical components for C because we have formulas that help us find magnitude and direction angles, but that requires us to know what the position vector is. It requires us to know what the horizontal and vertical components of that vector are. To find that, we need to figure out what is this here, right? The position vector for the airspeed, and what is the position vector for the wind. Okay, so let's tackle these things first, and then we can tackle what the position vector for C is. So I'm just using the horizontal vertical component formula to find horizontal and vertical components for the airspeed vector, for the plane's engine airspeed vector. The magnitude is 397 miles per hour. We're going to take the cosine of the direction angle, which is 40 degrees. No! Remember, 40 degrees is a bearing. That's different than the direction angle for a vector. The direction angle for a vector is this thing that I drew here in purple. It's theta. To figure that out, just notice that theta and the 40 degree bearing are complementary. So we can just do 90 minus 40 degrees to figure out that the direction angle of the plane vector, I keep calling it a plane vector. There's probably a better name for that, but whatever. The plane vector is 50 degrees. Okay, you calculate this stuff out, you find that its position vector is 255.2 and 304.1. Okay, we're going to do the same thing for the wind speed vector. 45 is the magnitude. The direction angle for the wind, since it's blowing directly east, is 0 degrees for cosine, 0 degrees for sine. Cosine of 0 degrees is 1, so B1 is 45. Sine of 0 degrees is 0, so B2, the vertical component, is 0, which makes sense given what it looks like here. So that is the position vector for the wind. Now, here is the cool part. To find the position vector for C, just realize that this plane vector has moved us horizontally to 255.2, right? So it's gone to here, right? And then the wind vector is just going to put us another 45 units to the right of that. So you're literally just adding the x coordinates to figure out the horizontal component for the resultant vector. In a similar manner, you're just going to literally add the y coordinates, the vertical components for each vector in the sum to find the resultant vector's vertical component. In this case, it's 304.1 plus 0, which is just 304.1. And that, ladies and gentlemen, is vector addition. You simply just add them component-wise, right? If vector A has position vector A1, A2, vector B has position vector B1, B2, you just add A1 and B1 and A2 and B2 to get the horizontal and vertical components of the resultant vector, respectively. That's how we define the sum of two vectors. You just add their like components. So back to here, here's all the information that we need, right? We found the position vector for C. We can get rid of, the plane vector and the wind vector. The only thing we need is on this picture now, minus the stuff that I just drew on it. So let's start off by finding the magnitude by just throwing it into the magnitude formula. I got that the true ground speed of the plane, right, is 427.31 miles per hour. So the wind, right, it's not straight up adding 45 miles per hour to the speed of the plane. It'd be adding 45 miles per hour if the wind vector was going in the same direction as the plane with a magnitude of 45. But that's not the case here, right? It's only kind of like a partial tailwind that we're getting. It is speeding us up, but not by 45 miles per hour, right? It's speeding us up by 30.31 miles per hour. To find the bearing, you have to figure out what the direction angle for this resultant vector is. So to do that, I noticed it's already in quadrant 1, so I just straight up took tangent inverse of vertical component divided by horizontal component to get 45.4 degrees, which means the bearing is 90 minus that. In this case, it's 44.6 degrees due north. So we're being blown off course a little bit. Now, of course, right, this shouldn't be cause for alarm when you're flying, right? Planes these days take all this information into account, right? So they never lose track of the direction that their plane's going or what speed that their plane's going. All the instruments on the plane handle that for them. But this is how we would calculate it, if we're just looking at this on the ground and we know, what the pilots have plugged in for the engines to go, what they've plugged in for the bearing. We can figure out what their true bearing is and all that stuff. Pretty cool stuff. Now, in the next video, we're going to talk about vector subtraction, which means we need to talk about scalar multiplication. And then we're also going to talk about the dot product. What's one way to multiply vectors? So hopefully you found this useful. If you have any questions, please leave a comment below. Thanks a ton for watching, and I'll see you in the next one.